Okay, so first topic that we covered in this class were isotopes and mass numbers. So we're going to start by just figuring out the protons and neutrons in this isotope right here. Okay, so we got 74 Br. And again, if you know how to do this, just ignore me, solve the problem, and then you can just check your answers afterwards. Okay. All right, guys. For number one, pretty simple. We got bromine. So if you look at Br on the periodic table, you'll see that it's 35 protons. And then you got the 74 up here. That is the mass number. And if you guys remember, mass number is protons plus neutrons. So you just need to do 74 minus 35. Should give you 39. Okay. Any questions on that one? Easy peasy, right? You will have a question again like this on your exam. So that's good. Then great. All right. I want you guys to try number 2 on your own. This one's a little bit worded differently, but the formula is still the same. We're still using the mass number formula. But the formatting is a little bit different. So try number 2. We'll go over it in like 2 minutes. All right, guys. So if you're finishing up, feel free to finish. You can check your answers after. But here we're looking at an isotope of calcium that has 5 more neutrons than protons. So the wording is a little different, but it's pretty easy to interpret. Calcium, if you look on the periodic table, is 20 protons. If you have 5 more neutrons, that means you have 25 neutrons. So the mass number is just the sum of the two numbers. So 45 Ca. Any questions on that? All right, so that's pretty much all the isotope mass number stuff. That's about as tough as it's going to get. Okay. All right, let's go on. So more isotope stuff. We're going to be looking at natural abundance and mass spectra. So I have a problem for you here. This is the natural abundance problem. So you got element with 5 naturally occurring isotopes, and the atomic masses, so the mass number is 5, 6, 7, 8, and 10. Okay, and that gives you the percentages for each of them. So take a look back at your notes. We went over problems exactly like this. See if you guys can calculate the atomic weight of the element using the percentages and the mass numbers. And then, if you feel comfortable, try drawing the mass spectra. Okay, so we went over problems like this in class already, so it should be a review. So take a look back at your notes, and then we'll go over them in about 3-4 minutes. Okay, so for this one, we got 5 different atomic masses, so kind of a longer equation. So we got 5, 6, 7, 8, 9, or sorry, 9, 8, and 10. And then we have our relative abundances in percentages. So first thing you got to do is you got to convert the percentages into a decimal. So divide by 100, or move the decimal twice to the left. So 50 becomes 0.5, 10 becomes 0.1, so on and so forth. And then you just plug and chug that into your calculator. You should get 6.4. And make sure you label the number AMU. Okay? Any questions on number 3, the relative abundance? Okay, again, you will have a question almost exactly like this on your exam. So just make sure you're comfortable doing those conversions, the percentages for the decimals, and then solving for the total natural abundance. Okay, mass spectra. For this one, you do need to memorize what's on the axes. So remember that the x-axis is the weight, so AMU, and then the percentage on the y-axis. And then you just need to put in the percentages for the respective weight. Okay, again, you don't need to be super precise, so no need to pull out a ruler or anything. As long as it's relatively the same, you should be good. What's up?
Even if the 9's not there,
yeah, if you omitted the 9, that's fine. I just do it because my brain would probably mess up if I didn't put the 9, so yeah. Yeah, just make sure you put a little gap between the 8 and 10. Great question. Okay, that's pretty much all of the isotope-related things. Any questions about that? Well, actually, no, there's a little bit more. Sorry. Shrimp. All right, let's go on, and this is going to be a type of problem. So this is actually pulled from one of the past AP tests, and you will have a question like this on your exam, and this was a little bit different because usually when we look at isotope, we're just talking about one element, right? However, for this one, we're going to be looking at the mass spectra of a molecule. Okay, so a little bit trickier, but the same principles apply. So one of the things about the AP test is a lot of times the questions aren't just about one topic. They pull different topics together and synthesize them into one question. So let's take a look at this. It's all stuff we've learned, but it's just kind of combining the topics. So it says that we're looking at a cyanide ion, which is Cn-, so carbon and nitrogen, And what we're going to do is we're going to assume that carbon has only one isotope, and that is carbon 12. Okay, so carbon can only be carbon 12 in this problem. Okay, it says to draw the mass spectra for a sample of cyanide if 20% have a mass number of 28 and 80 have a mass number of 30. So for this one, since it's really easy, I'm just going to do it with you guys real quick. So you got the percentage, and then you got the AMU. It tells you that 20% have a mass number of 28. So 28 right here. And then I'm going to write 29, but you don't have to. And then 30. And then it tells us that 20% have a mass of 28. So I'm going to do 20% right here. And that means this pillar is going to be this high. And then 80%, somewhere around here. It's about quadruple. Not exact, but that's fine. And 80% have a mass number of 30. So if you look exact same way that we do a mass spectra for just one element, even if you have a molecule, we're going to draw the mass spectra exactly the same way. So it's the percentage and the weight. All right, any questions on the mass spectra? Hopefully not too bad. Okay, this is where things change a little bit. It says, based on the mass spectra that you drew, what are the two possible masses of nitrogen isotopes in this sample? So this is a little bit different because here we're working with cyanide, right? We're working with Cn-. But for this problem, for part B, we are only looking at the isotopes of nitrogen. Okay, so what we got to do is we got to look at what we have for cyanide. We have cyanide, so Cn-, and then we'll put dash 28, and we have Cn- dash 30. So these are our two different types of cyanide. Okay, and the trick for this problem is to remember that carbon can only be carbon 12. There's only one isotope. So the two possible masses, the difference in the masses come from the nitrogen. So let me give you guys about a minute. See if based on that information you can calculate the masses of nitrogen. Okay, so see if you can find the nitrogen. All right, guys, so let's go over this. So let's start with cyanide 28. Okay, we said that carbon has to be carbon 12, right? And so that means nitrogen is going to, so it's 28. So the 28 is a sum of the carbon and the nitrogen.
So it would be 16.
Correct, yeah, you just do 28 minus 12. So the nitrogen here has to be nitrogen 16. Super simple, it's just subtraction. Okay, and then for the other one, again, carbon has to be 12, and that means that nitrogen here has to be 18. Okay, so those are the two isotopes of nitrogen. Okay, it gives you carbon has to be 12, so the difference is going to come from the nitrogen, and you just do subtraction. Okay, and again, you will have a question like this on your exam, so just keep that in mind. Okay, so for part C, it's asking how many neutrons does the most common isotope of nitrogen have? So we're going to look at our mass spectra. The most common one is going to be this one right here, the one with 30. And so the most common one has 18, or nitrogen 18. And so in order to find the neutrons, all we got to do is find the protons, right? So we got nitrogen 18. Nitrogen has 7 protons. So how do we solve for the neutrons?
You subtract the mass by the proton.
Correct. And so we get 11 neutrons. That's our answer. That's it. Okay, that's pretty much another variation of how to do mass spectra with isotopes, but also looking at it in terms of a molecule. Okay, so let's move on. Oh, sorry, forgot about that. Last part of this question. This is kind of touches on what we talked about before. If you look at cyanide, you guys see how it's Cn-, right? And we said the negative charge is caused by one extra electron, right? And so the question is asking, does the negative charge on the ion affect the mass spectra? I did mention this in class. Anyone remember the answer?
No.
Yes, no. Myro, why is it no?
Because it is too light. It is too small.
Exactly. The electron is very, or we can just say electron has negligible mass. Okay, so the electron is extremely small relative to the protons and the neutrons, so it's not even going to show up on the mass spectra. You can have one electron or multiple, it's not going to affect the weight in terms of the mass spectrum. Okay, and that is the end. I think I said that like 3 times already, but that is the end of the isotopes and the mass spectra things. All right, let's move on. The next thing we talked about, I think this was the end of Unit 2, is the stuff I told you have to memorize, the polyatomic ions. Who has memorized all the polyatomic ions? Great. All right, so make sure you have that chart handy somewhere on your Chromebook then. I want you guys to try 5 and 6 on your own. 6 is a little bit tricky. It requires you to have a pretty good understanding of the polyatomics, but I'll give you a minute to try that out as well. But try 5 and 6. 5 should be pretty light, and then we'll go over the 2 of them in a couple minutes. Okay, try 5 and 6. And if you don't have the polyatomic chart, make sure you just pull it up on your Chromebook somewhere. It's in the Unit 2 workbook. So for 5, you should know from the most common ion pattern that rubidium, it's in the first column of the periodic table, right? It's right here. So the most common ion is +1. You do need to memorize, again, the polyatomics that are important. Phosphate is PO4 3-, and you can see if you didn't memorize it, then you'd kind of be in trouble for the exam, right? Because if you didn't know what phosphate was, you wouldn't know the formula, and you wouldn't know the charge. But let's say that you did memorize for the test, you would get that. And then you would see that you need 3 rubidiums to balance out one of the phosphates. So the ionic compound that you make is Rb3PO4. Okay, so please make sure to memorize the polyatomic ions if you want to pass the test. If you don't want to memorize it, I don't really care.
Thanks, man.
Of course. Okay, and then the polyatomics, they become even more important for things like number 6. So it says select an element that may form a compound in this formula. So you got K2, you got a blank, and then SO4. Okay, so I think I pulled this directly from one of the old AP tests, if my memory serves me right. And basically, you just need to figure out which of these elements goes into that blank. So to do that, we need to figure out first the positive and the negative charges that we have in this ionic compound. So we got 2 potassiums. What's the charge for potassium's most common ion? 1. It's in the first column, so 1. Okay, so that means that all of the potassiums, they provide a positive 2 charge. Everybody see that? Okay, so what that means is the anion right here, okay, the blank SO4, it has to be 2- in order to balance out the potassiums. Okay, so we need to know our polyatomic ions. So basically what we're looking for is which one of these ions is going to have a -2 charge. And so you need to memorize them. And then the answer is going to be sulfur, because SO4 is 2-. This is called sulfate. And this is going to be your answer. Okay, ClO4-, I don't think you need to memorize this. This is perchlorate, and this is just -1. PO4, we just looked at it right here. That's 3-. That's phosphate, and so on and so forth. Okay, so just make sure that you guys memorize the ones that I told you to memorize. It will help you a lot, and especially in the next unit, Unit 4, we're just going to be using polyatomics like left and right. They're just going to come up in all these problems. You're going to just be expected to know them. They're not even going to ask you what is phosphate or what is nitrate. You're just going to be expected to know what they are. So just keep that in mind. Okay, let us move on to more ionic compound stuff. Oh, let me pause right there, though. Any questions on 5 and 6? Okay, so general premise makes sense, hopefully. Positive, negative stuff. Okay. Okay, so let's do 7. Okay. So 7, actually, let's pause. I'll have you guys try these 2 on your own. You can look at the naming rules if you'd like, but try to do it on your own, because on the test you won't have your naming rules on you. But try 7, and then that is going to be the end of all the Unit 2 stuff. We're going to move on to the Unit 3 stuff after 7. So if you take a look at Part A, you got CS2S. If you look at CS on the periodic table, this is cesium. Okay, now cesium, you don't need to put the parentheses behind it, because if you take a look, it is in the +1 column, right? And so since it has a most common ion, you don't need to add the parentheses or anything like that. So you just write cesium. S is sulfur, but since it is monatomic, it's just one element, you change the ending to IDE. And so that's how you get cesium sulfide. Okay, part B, you got titanium 4 sulfate. Titanium's in the middle of the periodic table, so that's why they included the parentheses. So that means it's Ti4+. Sulfate, again, you need to memorize your polyatomics, is SO4 2-. You're going to need 2 of the sulfates to balance out the Ti, and so you got to put it in parentheses and put a 2 afterwards. Okay, and that's going to be your formula. Okay, you will have several of the naming ones and interpreting the formula using the name on your exam. So again, please make sure that you guys get the polyatomics down. You do have the weekend to do that. So. All right, so that is all of the Unit 2 stuff. Any questions on any of the Unit 2? Okay. Either you guys really got it, or I'm just breaking your spirit right now. Okay. Hopefully it's the latter. Okay, let's move on. This one we're going to kind of combine everything together because the questions on the exam will pretty much combine the balancing, the stoic, the yield, and the limiting and excess. But we did this at the end of last class, so hopefully it's not too far from your memory. So we're going to do number 8. If it's a little hard to see, I'm sorry. Please just make sure you pull up the document on your Chromebook so that you can see the question more clearly. But I'm going to pause, and I'm going to have you guys try number 8, A, B, and C on your own because we ended off with this last class. So this is probably the freshest thing that we did. So you got a combustion reaction. Remember what combustion is. And then you're going to react, or you're going to be combusting methane. So write the balance equation first, then find the theoretical yield, and then figure out the limiting and the excess. So take about 5-6 minutes to do that, and then we'll go over it together. All right, guys, so let's go over the answers for number 8. It says that it's the combustion of methane, so you need to remember that combustion is when a hydrocarbon reacts with O2 and it produces CO2 and H2O. So keep that in mind. You will have a question that requires you to know combustion or the general formats. It's reacting with O2 to form CO2 and H2O. And then you just balance it. So 1, 2, 1, 2. All right, next we're going to find the theoretical yield of carbon dioxide. So CO2, you get 2 starting numbers, 10 grams of methane and 12 grams of oxygen gas. So 10 grams methane, 12 oxygen gas. And then you just calculate for CO2 for both of them, and you'll get 2 different numbers. However, if you remember, we always pick the smaller one because that's the one that limits the reaction. So the answer for part B is 8.25 grams because that's where the reaction is going to stop. We no longer have oxygen to keep reacting. So the limiting reagent in this problem is going to be O2, and then the excess is going to be methane, CH4. Okay, so that's parts A, B, and C. Any questions on that? Easy peasy? Great. All right, part D, I'm not going to scroll down right here, but part D is it tells you the actual yield of carbon dioxide is 5 grams. Okay, so we got to find the percent yield. So the percent yield is just a percentage formula. It's going to be 5 grams, the actual yield, divided by the theoretical yield, so 8.25 grams of CO2. And then you multiply that by 100%. You should get about 60.61%. If you round it to 61, whoa, that's fine as well. But something around there should be good.
Finding that excess, just put like the or whatever, and it is 5 grams.
Oh, you can just, if it asks you how much excess, then you calculate it. But if it just asks you for excess, just identify it. It's not going to ask you to calculate the excess. We don't do those problems on the AP test, or we haven't seen it in a long time. Yeah, great question, though. I was going to mention something I forgot. Oh, so a lot of people ask me, hey, Mr. O, what if you get like part B wrong? So let's say, for example, you did the calculations, and then instead of 8, you got like, I don't know, 17. Okay, let's just say hypothetically. And then you use that 17 number and you plug it into the bottom of part D, and then you get a different percent yield. So if you do that, for example, so some parts, the questions build on each other, right? So if you get an earlier part wrong, you'll get points off on that part. But if you do the setup correctly on the further later parts, then you'll get credit for that. So if let's say you got 17 for part B, and then you plugged in 17 here and got a different percent yield, you would get full credit for part C and D because you used the numbers correctly. Even though the answer was incorrect, you were basing it off what you thought was correct, and so you will get credit. So you only get penalized once for your mistake in the problems. Okay, so just keep that in mind. I know people wonder about that all the time.
And if you made a mistake, it'd be like 170-something%.
Yeah, I mean, sometimes you will kind of figure out that you made a mistake. If you had like a bigger actual yield than theoretical, then yeah, you can go back and change your answers, but sometimes it's not as obvious. All right, so that is all the stoichiometry stuff we are going to practice. Now we're going to get into, I think the hardest part of the exam is going to be the empirical formula stuff. So we're going to move on. Okay, so empirical formula. I'm going to do this with you, but if you feel comfortable doing it or you just want to try it out on your own, you can just kind of ignore me and just check your answers. But the hardest questions on this exam, just objectively, are the ones that require you to know empirical formulas pretty well. So we're going to do an easier one for the first one, and then we're going to end the class with, I guess, the hardest type of problem that'll be on your exam. Okay, but I wanted to show you how to go over it. So let's do number 9. Okay, percent comp of a mass, by mass of an unknown compound. It tells you that the molar mass is 90.078 grams per mole. Okay, so that is the molar mass. Now, if you see molar mass, what this tells you is it's basically telling you once you get the empirical formula, it's going to allow you to calculate the molecular formula. Okay, so it tells you how to go from empirical to molecular. Okay, but first we got to figure out the empirical. And then it tells you the percentages by mass. All right, so the first thing we want to do is we want to find the empirical formula. So we're going to do that in the color red. So if you guys remember, empirical formula, the first thing you want to do is you want to assume a 100-gram sample. And then you're going to take your percentages and turn that into grams. So 40.002 grams of carbon, 6.7135 grams of hydrogen, and 53.284 grams of oxygen. Okay, the reason why we do the 100-gram sample is because just an easy way to turn the percentage into grams, because if it's 40% of 100, it's 40. From there, you want to convert your grams into moles. So I'm going to stop right there, and I am going to give you guys about 2-3 minutes. See if you guys can convert all of your grams to moles here. Okay, guys. So the way to convert to moles is use the molar mass of each element on the periodic table. So carbon is 12, so 40 divided by 12 gets you about 3.33. The hydrogen is just 1, so you can just write the number again. And then oxygen is 16, so you divide 53 by 16, you get about 3.33. Everybody go to the moles? Okay, just one-step conversion. And then from there, what you're going to do is you're going to divide all of them by the smallest number, and that's going to be 3.33, and that'll give you the subscripts for your each element. So carbon will be 3.33 divided by itself, which will be carbon 1, so C. Hydrogen, 6.7 divided by 3.33, about 2, so it'll be H2. 3.33 divided by itself is 1, so you got this. So this is going to be your empirical formula. Okay, and so that's how you can find empirical formula using percent composition. Alrighty, any questions on that part? Again, you'll have a question like this. You'll have to you'll have to find the empirical formula using the percent comp by mass. Okay, one last step. We got to find the molecular formula. So I'm going to do this in blue now, just so we can kind of differentiate the two parts. Okay, molecular formula from empirical is really easy. First thing you want to do is just find the molar mass of the empirical formula. So carbon is 12, hydrogen is 1, there's 2 of them. Oxygen is 16, so you're going to add those up. So 12 plus 2 plus 16, that's going to give you about 30. 30 AMU. So the empirical formula is going to have a molar mass of 30. Okay, now it tells you that the actual compound is 90. Okay, so what we want to basically figure out is what do we need to do to get 30 to 90? How can you get 30 to 90? Yeah, times 3, which means in order to turn the empirical to molecular, just multiply the formula by 3. So it'll become C3H6O3, and that is your molecular formula. Really easy. Okay, now for these problems, just heads up, you will always get a whole number, so you won't get decimals for it. So if you got something where you'll end up with decimals, you did something wrong, so you can go back and correct it. Okay. All right, guys, and that is 90% of the problems we're going to go over today. We got one last one, and that's the hardest one. That's going to be on your exam. Any questions about the previous 9? Okay, we're going to take a quick 5-minute break before we go into the last question, and that will conclude our review. So take 5, and then we'll come back and finish. Okay, so for number 10, I'm going to ask everybody to just pull it up on their Chromebooks. I'm not going to have it on the screen just because I want as much space on the screen to go over the answers with you. It's not because there's a lot of work. Honestly, it's not too much, but a lot of the prep work, comprehending the question is where I want to spend some time writing it down. You guys don't need to write down everything when you do the exam, but I wanted to break down the question really slowly and detailed for you. So just make sure you have this on your Chromebook or share with the person next to you, because I'm just going to have the blank screen so that we can write down everything that's in the problem, okay? All right, so if you take a look at number 10, it tells you that you got a compound that has the elements C, N, and O. Okay, and it tells you that this sample is burned in excess oxygen and it weighs 1.2359 grams. So before we start, let's just start by, writing some stuff down. So first, we're looking at a compound that's C, we don't know how much, H, N, and O. We don't know the subscripts, so we're just going to leave it alone like that. Yeah. Is that hard to see?
Yes.
Oh, goodness.
Light mode.
That's fine. You know what? I'm just going to do it on here. I'll be boring. Sorry, guys. Is this better? C, H, N, O.
I mean, I feel like you could have done it on the dark screen and used yellow.
It's fine. Whatever. I'll stick with what I know. We'll make it work. Okay. So this is the compound. And it tells you that this thing weighs 1.2359 grams. Okay. All right, next thing it tells you is that it's burned in excess oxygen. Burning is a combustion reaction, so it's reacting with O2 gas. Okay, and if you guys remember combustion, what are the two products of combustion?
Water and carbon dioxide.
Correct, yeah. So you got CO2 and H2O. Perfect. So we know that that's automatically going to be made. Now, you got a nitrogen on the reactant side, so we're going to have nitrogen somewhere, but we'll get to that in a second. And then it tells you that the carbon dioxide that is formed is 2.241 grams. And then it tells you that the sample contains 0.0648 grams of hydrogen. That means that inside of this compound right here, there's going to be 0.0648 grams of hydrogen specifically. And then it tells you the third and final product is N2. So I'll stop right there. But that is pretty much a summary of all the information that is given to us in that first paragraph. Okay. So I'll pause. Any questions on what we got down? All right, so let's do part A. It tells you when the compound is analyzed for nitrogen only, the mass percent of nitrogen is found to be 28.84. Okay, so 28.84, and then it's basically asking how many grams of nitrogen are inside of the original sample. Now this part's pretty easy, right? Because it's telling you that the original sample weighs 1.2359 grams in total. It tells you that nitrogen is 28%. And so all you got to do here is multiply by 28%, so 0.2884. And that will give you the nitrogen. Okay, so 1.2359 times 0.2884. Okay, and so what we get for part A is we get 0.35, and I'm going to write that third one just to help out a little bit, 6, and we're going to label it grams of nitrogen. And that'll be the answer to part A. Okay, so part A, pretty easy. All right, so far so good, guys? Okay, let's go to part B. This is the one that it requires a little bit more thinking. But it says determine the mass in grams of carbon in the original sample, the 1.23 gram sample. And we're going to assume that all of the carbon in the original compound was used to produce CO2. So this last statement is very helpful because what it's telling us is that all of the carbon that was in here was used to make this carbon dioxide. And that is helpful because we know how much carbon dioxide was made, right? So what we can write down first is that there are 2.241 grams of CO2. Okay. So we know how much CO2 is made in total. So what we're going to do is we're going to analyze the CO2, and what we're going to do is we're going to figure out how much carbon is in the CO2. Because if we figure that out, since we know all the carbon came from the original sample, we can kind of just reverse it and just kind of assume that however much carbon's in here is the amount that was carbon in here. So what we're going to do is we're going to use the formula to do that. So what we're going to do is figure out the molar mass. I'll do it for you. It's just C plus 2 oxygens. It's going to be 44 AMU in total. So carbon dioxide is 44 AMU. Okay, so we know the total. Now we're looking at the carbon. We know that carbon is 12 AMU. And so what we can do is we can use these two values and the percentage formula to figure out what percentage of CO2 is carbon. And that's the trick here. Okay, so we're going to use the percentage formula to figure out what percentage of CO2 is just carbon. Pretty simple. You take the 12 AMU, divide it by the total, and that's going to give us our percentage. Okay, so about 27%. All right, any questions on that setup? Okay, we found the molar mass of CO2 and carbon, and we just divide them to figure out what percentage of the total is just carbon. All right, so what we're going to do now is we're going to take our percentage, and since we know that carbon dioxide is about 27% carbon, if we have 2.2 grams of it, all we got to do is take the 2.241 grams of CO2 and multiply it by the percentage. And that's going to give us the mass of carbon inside of it. So just multiply, so times 2.241, and that's going to tell us that inside of this sample of carbon dioxide, there is 0.611 grams of carbon. And that also tells us that in the original sample, the original chemical, there was 0.611 grams of carbon in there as well. All right, any questions on part B? Hopefully not too bad. Once you know the percentage thing, should be pretty easy to calculate the carbon in the original sample. Okay, part C. Part C is asking, they want you to find the mass of oxygen in the sample. Now, we just figured out carbon in part B. Okay, we figured out nitrogen in part A. In the original question, they gave us hydrogen. You guys think you can calculate oxygen? Yes? Maybe? Okay, let me give you a minute to try that out. See if you guys can calculate the oxygen that was in the original sample. All right, guys. So I just kind of summarized the information right here in the corner for you. Sorry, running out of space. But the compound is made out of carbon, hydrogen, nitrogen, oxygen. Carbon, we found out in part B, is 0.611 grams. Hydrogen, it's in the problem, is 0.0648 grams. The nitrogen is 0.356 grams from part A, and the total is 1.2359. So to find the oxygen, you just need to subtract all of them from 1.239, and I got an answer of 0.2041 grams. Everybody good with that? So that is the weight of oxygen inside that original compound. Okay, now you can see that we have the weight of every single element inside of that compound. So you just did subtraction. So you're going to take your total mass minus the carbon, which is right here, minus the hydrogen, which is given to you here, minus nitrogen, and that gives you the remainder, which is oxygen. Okay. All right. Everybody got the individual components written down? Because we'll need it for the next part, and I got to move down, so I'm going to delete the screen. But again, I am recording everything, so if you wanted a little help as you're studying for the exam, you can watch this video back, and then it'll help you solve the problems. Okay, but moving on to the last part. Okay, you guys probably love this now. We're going to do the empirical formula. Okay, so I'm going to pause right there, give you guys about 5 minutes, see if you guys can figure out the empirical formula of this compound. Okay, so try that out. It's the exact same thing we did in the previous problem. We're just doing it with the numbers that we just calculated. So the onus here is to figure out what the numbers were. So try that out, check with the person next to you, and then we'll go over it, and then we're done with the review. Okay, so for part D, we just take the numbers that we calculated in the previous parts. You don't need to assume a 100-gram sample because you already have the grams already, so don't need to assume anything. So we just need to divide by the molar mass, and it'll give us moles. And these are the values you get. Something close to that is fine. Again, your numbers do not need to be exactly the same as mine. As long as you're in the same ballpark, you're good. And then what you do is you divide by the smallest number, which is the 0.0128, and that'll give you these values around here for each of the elements. Now, if you notice, luckily they are all very close to a whole number, right? So that means that the empirical formula is going to be C4H5N2O, and that is your empirical formula. And that is it, guys. Congratulations. That is end of the review for units 1, 2, and 3.